Welcome everyone. Alive, okay. Welcome everyone. Thank you for tuning in. I am very pleased to welcome you all to our now ninth webinar in the Rain Enhancement Hub series hosted by the National Center of Meteorology and organized by the UAE Research Program for Rain Enhancement Science. My name is Sarah Alamiri and I am a program officer for the UAE REP and I'll be moderating today's session. I am very pleased to welcome Dr. Salman Khan from Mohammed bin Zayed University of Artificial Intelligence with us today to present a session titled Future Trends in Rain Enhancement and Tackling Climate Change via Advanced AI Solutions. Dr. Khan is an associate professor of computer vision. Prior to joining MBZUAI, Dr. Khan was a senior scientist with the Inception Institute of Artificial Intelligence and is an honorary lecturer with the Australian National University since 2016. Dr. Khan's primary research interests include computer vision and machine learning. He has been actively working on learning from limited data, zero and few shot learning, adversarial robustness of deep neural networks, and continual lifelong learning systems for computer vision problems. Dr. Khan will present and discuss future trends in rain enhancement and tackling climate change via advanced AI solutions. Audience, please go ahead and type in your questions at any time during the webinar using the chat box. We'll be sure to address your questions during the Q&A session after the presentation. Over to you now, Dr. Khan.
Thank you, Sarah, for your kind introduction. So, hello, everyone. Hello, and welcome to this webinar series organized by National Center for Meteorology in UAE. So today I'm going to talk about the future trends in rain enhancement and tackling climate change using advanced AI solutions. And just as a very quick introduction, my name is Salman Khan. I'm one of the faculty members in the Mohammed bin Zayed University of Artificial Intelligence. So before we begin, I would just like to very quickly introduce some of our work which have been carrying out as part of Intelligent Visual Analytics Lab. And as a core focus of this lab, we are looking into visual imagery and also multimodal analysis, which basically revolves around language as well as vision using artificial intelligence algorithms. So as part of the key application areas, we have been looking into remote sensing and earth vision problems. And here I have just put down two key application projects we have been undertaking right now. So on the left, you will see our joint project, which is as part of a consortium towards AI-enabled efficient cloud seeding algorithms. And here the motivation is that, as you all know, water scarcity is a major global issue, and timely rain can act as a natural source of fresh water. And the challenge here is that only a fraction of clouds are typically suitable for seeding operations. As part of the solution, what we have proposed is near real-time diagnosis of cloud cluster seedability using artificial intelligence algorithms. And down the road in this talk, I will explain some of these algorithms in a bit more detail. So here we plan to actually use different data sources involving both operational meteorological data as well as radar and satellite data. And the benefit that we expect is actually enhancing the rainfall through cloud seeding and more effective utilization of resources as well during these rain enhancement initiatives. If you look at your right, so this is just a very quick summary of our joint project together with IBM, where we are looking into identifying and mitigating these urban heat islands. So these are areas which are excessively hot in our urban environments. And the goal here is to see how we can use big data as well as artificial intelligence for identification of these urban heat islands, and then also studying their effect on common people, and also pinpoint factors which are contributing to these excessively hot points. And down the road, the goal is to actually provide recommendations in terms of how these heat islands can be mitigated effectively. So with this very short actually intro to some of the work we have been doing in the lab, I would like to jump right on to our today's topic, which is around rain enhancement and climate change. How we can tackle these problems using artificial intelligence. So climate change is characterized by rising global temperatures and extreme weather events, as well as biodiversity loss, as poses a significant threat to ecosystems and human societies. And in response, rain enhancement and also weather modification techniques in general, including cloud seeding, actually are explored as a means to mitigate the water scarcity and adapt to the changing precipitation patterns. So the overall goal is to see how we can utilize these advanced technologies in terms of weather modification to combat some of the adverse effects we are getting due to climate change. And the question is how AI can actually come into this picture of climate change mitigation, also weather modification. So as you know, AI offers transformative solutions across various sectors to address climate change, and this is in part fueled by the excellent data analysis capability AI offers. Also in terms of the capabilities in terms of predictive modeling, so we can predict how, for example, weather patterns or climate patterns are going to change in future, and also towards automation of a lot of, for example, our industrial practices as well as our farming practices and so on. AI can help us enhance efficiency of these operations and also helps us optimize certain operations, especially, for example, for renewable energy deployment. It is really necessary to understand the supply and demand cycle, and AI can help us here in terms of analyzing all of this data coming from IoT or sensors, which are ubiquitous in our environment, and can provide recommendations into how these renewable energy options can be integrated into the grid. And similarly, AI can help us improve carbon capture technologies, even in terms of identifying and discovering new materials that can help us with carbon capture technologies, and also towards contributing significantly to global mitigation efforts in terms of carbon capture. So today I will discuss two key directions here. So how AI can help us address climate change, and also towards optimizing, for example, weather modification tasks as well, especially with a focus on rain enhancement. So I would like to start with optimizing cloud seeding operations. So this is just a glimpse of the proposal which was recently funded by the National Center for Meteorology as part of their rain enhancement program. So what I would like to do is that quickly give an overview of what we intend to do using advanced artificial intelligence algorithm. So the goal here is to see how we can use actually machine learning based real-time algorithms for quantification of cloud seedability. So we want to not only know which clouds and where are these clouds, but also we want to actually have an estimation of what is the estimated seedability of those clouds. And this is the main distinguishing factors of this project. And the starting point is to see how we can collect and process this heterogeneous data coming from multiple sources, which includes both meteorological as well as satellite and radar data, and see how this data can be actually fused together to have actually a more comprehensive outlook in terms of understanding the cloud physical properties. The third step is to see how we can simulate the cloud microphysical properties and precipitation forming process. And using these simulations, we'll try to train our artificial intelligence algorithms to make predictions on seedability. And because this is done in a simulation, so we'd like to eventually do a transfer learning, as I will talk about a little bit more detail down the road as well. So with the inference on precipitation forming process and suitability using deep learning architectures, we hope to actually obtain good estimates of suitability and real-time targeting of seeding operations, and that would be a really a fruitful outcome for this project. So just to summarize, the main specific objective of this project is to obtain near real-time cloud microstructure, as well as droplet concentrations and height for rain initiation, and also glaciation temperatures. And the second main theme is to see how we can obtain the near real-time precipitation forming processes. And the third main step would be to actually see how we can have estimations of cloud seedability using different seeding methodologies. And based on this, then we hope to provide a tool, an analysis tool, which using artificial intelligence and given an existing cloud system, it can provide recommendations on to whether we need to seed these clouds and what will be the potential seeding effect in case we decide to seed these clouds. So this is kind of a glimpse of the overall project. So in this flow chart, if you start from, there are in total 10 tasks. And if you start from left, top right, top left side, you will see that, we are aiming to start from an observational data where we'll be looking at both satellite as well as radar and meteorological data as well. And in this process, the second key step is to see then how we can obtain the observed data from the satellites, and this will really help in retrieval and validation of cloud microphysical properties. And the third task here down the road is for us to see how cloud physics aircraft data analysis can be used for validation of these cloud simulations. And with the cloud simulations using SVM platform in task 4, we'll try to see how the previous well-documented cases as well, which have been sometimes also provide aircraft-based cloud measurements, and we'll like to use those cases for validating our analysis and observations. So with this, in task 5, we will like to look into the satellite channels, which will be simulated with the radiative transfer model on the cloud simulation, so that the satellite observations can be related to the model simulations, right, for variables which are not observed directly. And again, this will help us validate against the observed satellite parameters. In task number 6, because not all satellite data has the same resolution, of course, high resolution data is extremely valuable for us. So in this case, we will be looking at again artificial intelligence-based algorithms for super resolution of the satellite imagery. So how we can train from coincident high and low resolution satellite imagery to actually in the inference time take any low resolution image and convert it into a high resolution satellite image. And this input actually will be very valuable for the next tasks. For example, if you look at task number 7, here we are looking to actually simulate the cloud seedability under different seeding methodologies and background aerosol conditions. But with this simulation-based model, we would like to transfer it into observed satellite data in task number 8. So in task number 7, basically, we are working with the simulation data. However, with domain transfer, we will try to actually bridge the gap between the features in real world, real domain, and the simulated data in task number 8. And in towards the end of this project, if you look at task number 9 and 10, basically we are training these machine learning deep neural networks on the seedability data and the input data that we actually fused and processed initially. And task number 9 is basically just trying to have these estimation of seedabilities again on the simulated data. And task number 10 actually aims to transfer this and validate it on the observed satellite and other data to estimate how the seedability estimates are effective. So this is just a very short summary of the whole project pipeline that we intend to undertake. But the core 2 areas I would like to discuss a little bit in more detail, which specifically relate to the artificial intelligence algorithm that we are planning to work on. So this relates to task number 6, which talks about the super resolution, and then the next task which talks about the domain adaptation, which is task number 8. So I will just like to, in a couple of next slides, try to go a bit more detail about what we want to do with super resolution and domain adaptation procedures. And if we talk about super resolution, our group have been, actively publishing in this topic for the case of natural images for the last 5-6 years in the top venues. And here I'm showing just one example from the recent CVPR 2022. So this is the flagship conference for computer vision and pattern recognition research. And here we presented a burst image restoration and enhancement framework based on deep neural networks. And this paper was also one of the finalists for the best paper award at this conference. So when we talk about burst image restoration, it is nothing but a shot of multiple images. And we believe this can also be useful because for the case of satellite images, typically we also have multiple shots, but taken at different time steps. And in this network, actually, there are three key stages. We start from an edge boosting feature alignment because many times when we are taking multiple shots for the natural images, the edges are not well aligned. And in the first case, we want to actually have a good feature alignment to remove any noise and interframe and both spatial and color misalignments as well. And in the second stage, we have a burst feature fusion scheme, and this is quite an efficient fusion scheme because it tries to exchange information across all of these burst shots that are input to the model in a much more efficient way. And as a third step, we look into adaptive group upsampling module, which progressively increases the spatial resolution, and while also merging this multi-frame information. So it keeps on looking, into quadruples of these features, and then progressively combines all of them in an adaptive manner through the hierarchy of this architecture. So this is a generic framework, and we expect it to be directly applicable actually to satellite images as well. And the inputs in this case would be the satellite low resolution imagery, and the intended output would be the satellite imagery with high resolution properties. So the second thing I just wanted to touch base from the artificial intelligence side is domain adaptation. So because as I mentioned earlier, we would be initially working with the simulated data, and the simulation data can, for example, come from the simulations of MSG and MTG satellite images. And we would be training because they're getting the seedability and all the physical properties of the clouds is very straightforward. And then the goal will be to see how we can adapt or bridge the gap between the reality and the simulation. So how we can adapt these models which are trained on simulated data, or features which are actually obtained from the simulated data to the observed real data as well. So in this process, again, I would like to correlate it with some of the recent work we have done in the lab, and this is a paper led by one of our postdocs in the IWell lab, and it actually looks at a similar problem, but for natural images. And in this case, these natural images are coming from source and target domains. And for example, the source domain can be observation from one sensor, target domain can be observation from another sensor, source domain can be observation from under one set of conditions, for example, day kind of conditions. The target domain can also be different environmental conditions as well, or weather conditions as well, for example, foggy environment, or the nighttime imagery, and so on. But the main goal is to see what we would like to do here in perspective of the rain enhancement project, is to see how the real and simulated satellite imagery can be aligned together well using domain adaptation. And the goal here is to see perhaps using an adversarial learning classifier like we did for this case, to see how the features can get indistinguishable for the model, so that we are sure that they are getting and actually demonstrating similar kind of behavior in a certain feature space. So the third main step would be how we can use deep neural networks for seedability forecast, because we are not only interested in actually identifying the location and the clouds that should be seeded, but we're also interested into how the seedability will look like once clouds are seeded. So based on that, again, we plan to use UNet kind of deep network, which can take in the input images of, for example, the satellite images of these clouds, and predict, for example, the forecast for the seedability. And the goal is to also not only just predict the cloud seedability, but also predict certain verifiable, interpretable variables as well as auxiliary predictions from the model, so that we can verify, whether the model is actually grounding its knowledge in physical reality or not. And these variables are actually very easy to then verify, and this may include droplet size distribution, uplift velocity, and available CCN as well. So the second key area where we think AI is already making a lot of news, and in future probably will be getting more relevant, is weather prediction models. And in this case, the main motivation is that early forecasting of adverse weather events is extremely useful, and especially for the Middle East region, which is also very susceptible to climatic effects and shifts. It is even more relevant. And the challenge here is that typically the existing forecasting models are depending on slow and rigid physical models, which are not as adaptable to the newly emerging data. And it also is sometimes difficult to integrate new and diverse climatic data within these models easily. And they're also typically slow when making these forecasts. So this is a common issue with numerical weather prediction models, that in terms of making forecasts, typically they require a lot of time for the simulation. Now, in contrast to NWP models, with the artificial intelligence models, the benefit here is that you can run multiple simulations of different kind of scenarios that might happen. And recently, we have a number of models actually which try to delve onto this problem. And one of these is Pangu Weather, which is we are showing some sample outputs on the ERA5 dataset. And as you can see, in terms of forecasts, these forecasts from the AI model are very close to the ground truth, and sometimes they're even better than the operational IFS forecast models as well for forecasting time, which is quite significant, roughly 3 days, 3 to 4 days in this case. So again, this is, these are some of the models outputs. If you look at the bottom, these are the models that we're trying to adapt for the Middle East region in our lab. And in this case, it is we are showing predictions for just 3 variables, which relate to the temperatures and geopotential at different levels. And the bias actually shows, the amount of difference between the ground truth and predictions. And of course, the spatial resolution is a bit low. That's why, these outputs are a bit blurry. But we are also training models which are at much better resolution. And the goal is to see how we can improve forecast for these extreme weather events, specifically for the Middle East region. So these are localized weather prediction models. And just to highlight, what benefit we can get from these. So if you look at, these at the prediction map, which is shown for the typhoon Kongri and Yudu, so the ground truth is actually what happened is shown in black. And if you look at the Pangu weather forecast prediction, and compare it with the ECM weather forecast model, you can see that the AI model prediction aligns much better with the ground truth in this case. So again, for predicting extreme weather events, it could be really significant for tackling climate change and reducing its adverse impact on local populations. So with this, I would like to jump on to what more is possible. So I just discussed, briefly 2 important applications on which we are already working on in terms of rain enhancement program, and also the weather forecasting models as well. However, the important question is perhaps going forward, what more is possible using artificial intelligence. So one of the key areas we believe will attract more attention, and it's already attracting a lot of attention from UAE and specifically from NCM as well, is in terms of intelligent, sensing bodies or agents, for example, drones, which can do this, this real-time decision making for cloud seeding. And there are some existing programs, actually launched in UAE itself for having utilization of these drones and so on. But right now they have been used for typically to deliver these electric shocks to bring together the rain particles and perhaps promote rain. However, we believe using AI algorithms, similar system or platform could be made even more intelligent as well. So it can make actually decisions on where to actually seed on the fly, and similarly also how to adjust to changing weather conditions during the mission itself, because the mission typically takes a fair bit of time as well. And similarly, it can make more intelligent choices in terms of which seeding agents can be more precisely and effectively used in a given scenario. The second key area where we believe might benefit from artificial intelligence is that of enhanced simulation of cloud physics. So as we know, the cloud physics is quite complicated, and on the right, if you see, there is one of the models in terms of how clouds evolve and what are the factors which are kind of governing different properties that these clouds exhibit. But this is a fairly complex process which is involved in the formation and precipitation process. But using artificial intelligence, and if we have huge amounts of data, these problems can be understood from using data-driven models. And the goal is to actually see how simulations can predict the outcomes of cloud seeding, and this can downturn, as a downturn effect, it can help guide more effective seeding strategies as well. And there are already some works, for example, this DeepMind work on actually simulating the fluid motion. So it is actually training a graph neural network to understand and model this complex physical phenomena which governs with fluid motions. And this is a similar thing that your normal physics-based simulation engine would also do, but in this case, this is just a data-driven model which is trained with huge amount of data, and it exhibits simulation behavior very close to the actual physics-based model as well. And in this case, it also demonstrates very good generalization, which I believe is the key when we come to cloud physics simulation as well. So the third key area can be actually combining the benefits of Internet of Things platforms together with artificial intelligence for advanced environmental monitoring. And this can range from actually, sensing our soil conditions in terms of what is the moisture there, nutrient levels, to atmospheric conditions. So what have been the previous trends in terms of weather, and for example, the precipitation patterns and so on. What are the agriculture schedules in a country, in a city, in a local zone, and then use all of this information and together with the AI models can help predict the precipitation patterns to evaluate how effective the rain enhancement project will be, and how the water resources can be actually their management can be optimized better as well. So again, in terms of customizing the rain enhancement solutions for a particular region, keeping an outlook into all the factors ranging from atmospheric conditions to soil conditions, and the patterns of the local population, as well as, for example, the agriculture schedules as well. And the fourth and last key area I would like to just quickly discuss is again in terms of having long-term climate forecast and long-term climate planning using predictive analytics fueled by artificial intelligence to actually incorporate again that capability in the planning of rain enhancement plans and actually schemes as well. And there have been recently a number of such efforts in terms of predicting long-term climate forecasts using AI models, and these include, for example, ForecastNet, climates from and astronomer models from Microsoft, DraftCast from Google, and Pangu Weather as well. And all of these weather prediction models based on artificial intelligence actually aim to have these forecasts from both from ranging from short term to long term. And on the right, you can see the example forecast that we are getting from the IFS, as well as the ground truth top left corner, and then these two outputs from GraphCast and Pangu Weather, which are two state-of-the-art weather prediction models based on artificial intelligence capabilities. So again, with this predictive capability, we believe that this is essential and crucial for long-term planning of rain enhancement strategies, because if we know better about how the weather patterns are going to change, these projects can be planned in a much more efficient way. So just to summarize, I started with how AI can be effectively used for enhancing cloud seeding operations. And this can range from having better estimates of seedability to forecasting the location and timing of the seeding operations as well. And the second key area that I highlighted, where our lab is also actively focusing on, is in terms of weather prediction model based on AI. But these are localized and region-specific weather prediction models that can help us look out for accuracy in terms of prediction of the weather patterns, ranging from the nowcasting to short-term forecast as well as long-term forecast up to 10 days in advance. Which again, as we discussed, can be really helpful in terms of minimizing the adverse effect of climate change. And the third key idea we discussed today was how we can take benefit from artificial intelligence to tap onto several potential use cases, which can be of great value in a lot of different applications, where sensing can be combined with artificial intelligence to create more impact. And some of the examples that we discussed today included, improved simulations of cloud physics, the predictive analytics for climate modeling, and similarly having a ubiquitous environmental monitoring platform using IoT sensors and artificial intelligence for improved localized weather enhancement projects. So with this, I would like to thank you, and if you have any questions, we'll be happy to take them.
Thank you very much for the insightful presentation, Dr. Khan. We received a few questions from our audience to address during our Q&A session over the next 15 minutes or so. The first question: AI has been widely used in the post-processing and calibration of the output from physics-based climate weather models. Beyond post-processing, emerging attempts are focused on replacing physical parameterization altogether with deep neural networks fed by long-term historical data. Do you see the concept of the exclusive AI-based climate/weather forecasts taking shape over the next 10 years? Or is a hybrid physics-guided AI approach would be the most promising path?
Thank you, Sarah. I think it's a very deep question. So actually, I think if we look at the trends so far, definitely in the recent years, there have been shown great potential of these totally data-driven AI models over the physics-based, simulation models for making these forecasts. And as I was just discussing, we have numerous examples coming from research labs, ranging from, for example, ForecastNet from NVIDIA to Climax and GraphCast from Google, and similarly there are models from Amazon, and the Pangu weather examples we looked at. So there's a very clear, trend towards people moving on to and showing actually the capability of data-driven models, which do not use the physics principles there are no physics underlying principles, but these models are typically trained on huge amounts of data. and they have been able to do pretty good in terms of making estimates. And now there are again some pros and cons of these models. So one of the limitation you can say is that there is still a lack of transparency, or these are typically black box models, and it's not clear that what exact, for example, a parameter combination actually led to a particular prediction, right? And what are the actually human interpretable features which are leading to a certain kind of outcome from these models. So I personally believe that perhaps it would be a combination of both, because both sides have to offer certain advantages. So if you look at, for example, physics-based simulation models, they are interpretable. We know the maths and physics that goes underneath, and these are well tested and well developed models which have been studied for quite a long time. um, and so there is definitely some benefit there. And then there is also an extreme long history of science that goes underneath these models. But for on the other hand, we have artificial intelligence models, which can be very efficient in terms of forecast. So the efficiency aspect is a great plus. However, as I mentioned, there are still a certain concerns around some of the inherent biases in these models. They may not, adapt well to a particular region itself, because they have looked at the global data itself. It's hard to interpret their outcomes as well. So I think probably we will see a combination of these two, to have the best of both worlds. And we are also seeing this in the recent even data-driven models as well. So there's a glimpse of actually incorporating physics-based actually toolkits as well, to improve and enhance the capabilities of these models, and also to catch certain error modes in which these AI-based models can easily get into.
Thank you so much, Dr. Khan, for that answer. Um, the second question asks, what does the future of AI-driven weather forecasting look like, specifically for the Arabian Peninsula region? What are the associated challenges in unlocking its potential for the complex arid and hyper-arid environment of the Arabian Peninsula?
Okay, so actually, if we look at Arabian Peninsula, there are, you can say the climate properties are a bit distinct, because if you look at the geography, the air patterns, the climate change happening around this region as well, it is kind of unique in comparison to any other region in the world. And again, there are unique challenges. For example, water scarcity. If you're talking about extreme heat waves, these regions are likely to be with actually one of those regions which are affected immensely by the climate change and the rising the temperatures and so on. So in terms of weather prediction models, I mean, if there are abnormalities in certain kind of predictions, then it gets hard to predict those if there are no examples of that in the training data. So from the perspective of, if we talk about the weather prediction for specifically for EME region itself, because of its unique conditions, and how the patterns are changing, I think one of the key challenges is that it is really hard to predict these abnormalities without having good amount of instances, because these AI models typically rely on what they have seen already in the training phase. So that is one of the key challenges. And the second thing is also, if we look from the climate science perspective, and again a disclaimer that I'm not a climate expert, but what we have seen recently is that there have been certain heat waves, and sometimes storms and extensive rains, which emerge out of phenomena which is not very well understood or well modeled in these forecasting systems. And then again, this is a challenge for climate scientists to actually see how these weather prediction models can be improved to take into account those variables as well.
Thank you so much, Dr. Khan. The third question asks, how can leveraging AI in both the short and long term inform climate change mitigation and adaptation strategies?
Right. So, in terms of, long term again is a bit subjective. So, the current models are typically, looking at 5 to 10 days as a long term prediction, and it is really hard to go beyond that at the moment. But in terms of short term predictions, definitely, if there are certain storms or hurricanes which are going to, for example, strike shoreline, then in terms of short-term predictions, you can always help predict their outcomes on the local populations, right? However, in terms of long-term impact, I think we can also look into historical data. So, like we have been doing for the joint project we have together with IBM in terms of analyzing decades of the heat or the thermal bands of the satellite imagery coming from Landsat and Sentinel-2 to try and understand how this long-term, for example, seasonal changes of temperatures are going to look like maybe in the future. And that is something which is perhaps possible through not exactly the weather forecasting models, but kind of the foundation models, which have been trained in a self-supervised manner with a huge amount of this previous historical data in terms of predicting several variables, that may range from air quality measurements to, for example, PM2, 2.5, PM10 kind of measurements, to precipitation, temperature, humidity patterns as well. And in terms of, if the self-supervised training is done with intervals which are pretty long, then they can typically do a good job in terms of forecasting those long-term patterns as well in terms of seasonal changes and how these climatic variables are going to shape up. So I think it can play, AI models can play a very significant role in this process, and it needs actually a lot of the synergy between cross-disciplinary scientists who are perhaps working on their own research topics, but then you can get the best out of these specialized domains when you put together a team of diverse specialities, coming from um, Earth observation analysts to climate scientists to artificial intelligence researchers and so on. And I believe NCM and Train Enhancement Program has been pivotal in actually bringing some of these teams together.
Thank you, Dr. Khan. You showed a use case example of BitNet for generating a high quality RGB image from a raw image burst. How effective is BitNet in the case of satellite imagery, especially for complex cloud structures?
Right. So this is a question, which we want to test as part of this project, which has just been awarded. So we haven't run extensive experiments on this. However, we have looked at generic satellite images, and for the natural looking images, for example, the observed RGB images coming from, for example, optical sensors and satellites. Typically, we can do a fair good job in terms of super resolving those images. However, specifically for the case of cloud images, how these microstructures will, emerge once we super resolve them to different levels, 2x, 4x, 8x. This is something which remains to be seen. However, just I would like to mention one thing that BIPNet originally works with raw burst sequences, which are the raw images that these optical sensors gather. And for the case of satellite images, typically we don't have access to those raw images. However, the same architecture pipeline can be effectively used for the just the RGB comments as well.
Thank you so much. Our last question here. UAE Rep is working currently with the Mohammed bin Zayed University of Artificial Intelligence team and awarded a project titled Identification of Cloud's Microphysical Suitability in an Actionable Manner. Could you please briefly expand on MBZUAI's contribution to the overall project?
Thank you, Sarah. So, as I mentioned, so we would be actually leading on the three key tasks. And the first one was, as I explained during the presentation, the super resolution of cloud images that are coming from the MTG and MSG satellites. So first part is super resolution to have more detailed properties of these cloud structures. And the second key task we would be contributing to involves domain adaptation. So the first goal is to train these models on simulated data, and then once we move on to the real observed data, how we can bridge the gap between these two real and simulated domains. So that is the key second task. And then the third task is to train deep neural networks for predicting and forecasting suitability of cloud structures. So these are the three key tasks that we are aiming to contribute to.
Thank you so much for answering that, Dr. Khan. We appreciate it. Thank you very much, Dr. Khan, for presenting and discussing the role of AI and advanced technology in improving our understanding of atmospheric sciences and better utilizing them and enhancing and modifying the weather. You broke down multiple complex topics where AI can be effectively leveraged, including rain enhancement operations and research, climate change mitigation, and extreme weather forecasting. Thank you very much for presenting your insightful work, Dr. Khan, in our ninth Rain Enhancement webinar. It's been a great honor and pleasure. To our audience, this webinar is recorded and will be available on our website for those who missed the live stream. I encourage you all to attend our next webinar, which will advertise on our channels in the near future. Thank you very much for everyone who tuned in, and I wish you a great rest of your day. Thank you.